Alright, picking up here where we left off, this is an example of an AP problem where they give you the starting reaction and they want you to write a half reaction from it. So in this reaction we're decomposing hydrogen peroxide and they want us to write the oxidation half-reaction. So again, to figure out who's oxidized or reduced, we have to have those oxidation numbers. So let's start there. Here we have hydrogen peroxide, and so this is one that they'll use often just because people forget the exception, and so it's an easy way to trip people up. So peroxide has an oxidation number for oxygen, remember, of -1 instead of -2. And then hydrogen is +1 when it's with nonmetals. Over here we have water, so we have oxygen in water and it's not peroxide anymore, clearly. So the oxygen will be -2, and then the hydrogen will still be +1 because we're the non-metal. And then we have oxygen by itself as an element, and any element by itself with no charge has an oxidation number of 0. Very good. So, picking up from there, they want the oxidation half. So they want to know the loss of electrons. So from -1 for oxygen, which of these products would represent a loss of electrons? In water, the oxygen goes from -1 to -2, so that's going down. So it must have gained an electron to do that. But in the oxygen gas, it goes from -1 in peroxide to 0. And so that -1 to 0, that is your loss of electrons. -1 to -2, that would mean you gained an electron. So this is the half we're going to focus on. So we're leaving out the water, and it's just the peroxide going to the oxygen gas. So that's going to be our start for our half reaction. All right. Our next step, step 2, is to balance any elements that are not hydrogen or oxygen, but that's all we have in this reaction. Step 3 is to balance the oxygens by adding water. Here we have 2 oxygens on the left and we still do have 2 on the right, so that's done. In step 4 we balance our hydrogens by adding H+. We have 2 on the left, so we'll need to add 2 H+ on the right hand side. And then step 5 is to balance our charges by adding electrons. This is the oxidation half, so if I've written it correctly, I should need electrons as products because they should be given off or lost, not reactants. So on the left-hand side, we have a total charge of 0, while on the right-hand side, we have a total charge of +2 from these 2 H+, and then oxygen doesn't have a charge, and then again on the left, we have a charge of 0. So 0 on the left, +2 on the right. We need the +2 to come down to 0, so they'll be equal. So to get +2 to come down to 0, that's going to take 2 electrons, or 2 negatives. So we'll put 2 electrons on our product side. And that would be your oxidation half reaction. Half reactions should always include electrons. And then when you put 2 halves together for the final reaction, the electrons should always cancel. If you'll notice here, in this half reaction, we have hydrogen, but that hydrogen, H+, doesn't appear anywhere in the complete reaction. And that's because when you put the 2 halves together, the other half must also have hydrogen in it, and so they cancel out, just like the electrons would. Okay, so that's just an example of a problem you could encounter on the AP exam. All right, now we're going to talk about the same sort of reactions, so redox reactions, but they could occur in what is called a basic solution. So if you recall, previously we were talking about acidic solutions, and acidic solutions have a lot of H+ in them. But that is not true for basic solutions. Instead, they have a high concentration of OH-. So for basic solutions reactions, we're going to balance them the exact same way, but we'll just have another step at the end because we have to account for the fact that there's extra OH. There's not really extra H+, as there is in an acidic solution. All right, we're going to skip this slide and move to the example. So we have magnesium sulfite mixed with potassium permanganate. Here, our polyatomic ions are going to react with each other, and the metals are going to be spectators. You would not be required, again, to predict this. So we would give you this kind of skeleton equation, and you might be asked to balance it. So if you look at this one, you might kind of start out thinking that you could balance this by adding just coefficients, right, and trying to get your oxygens to balance. But you would quickly run into kind of a roadblock. It's almost impossible here to get your oxygens to balance just using a traditional method. And even if you did, your charges wouldn't be balanced. Okay? So another clue that you might need to use the special procedure is if it says basic solution. So recall before that if it said acidic or acidified, that might be a clue that it needs a special balancing technique. This is also true if it has the term basic solution in front of a balanced equation that we're working on. Right? So we're going to start with our big equation and narrow it down to our reduction and our oxidation half reactions. So we need to know who's oxidized and who's reduced using the oxidation numbers, of course. So we have oxygen, which is -2, and there's 4 of them, which is -8, and we need to add up to -1 for permanganate. So what can I put with -8 to give me -1? Manganese must be 7. On to sulfite. Oxygen is -2, and there's 3 of them, so that's -6. What do I put with -6 to get -2? That would be a 4. Over here in manganese 4 oxide, we've got -2 for oxygen. This is not peroxide. That's -4, so I need a 4 because there's no charge here, so they must add up to 0. For our sulfate, -2 for oxygen, that's -8 because there's 4 of them, so this has to be 6 to add up to -2. Alright, I encourage you to pause and go back and make sure that you know where oxidation numbers come from and that you can figure those out on your own. From here, we need to know who was reduced. That means their oxidation number went down because they gained electrons because we're doing the reduction half. So if you look at manganese, it's got a 7 on it, and in the product side it has a 4. So our manganese was reduced. When we write our reaction, we use the whole compound. The permanganate goes to the manganese 4 oxide. So there's our half reaction to start. All right, step 2, balance any elements that are not hydrogen or oxygen. Well, we have 1 manganese on both sides, so that's done. Step 3, balance oxygens by adding water. 4 oxygens on the left, 2 oxygens on the right, so we need 2 more oxygens. There's 2 waters to balance our oxygens. Step 4, balance by adding hydrogens. So we have no hydrogens on the left, but we have 4 on the right. So we'll need 4 on the left, 4 H pluses. And then finally for our electrons. So let's look at our charges a little bit more carefully. This has a -1 charge. And here we have 4 positive charges, so that's a 3. 0 right here, and 0 right here. So 0. 3 is the higher value. I need to get it down to 0. So how do we get 3 down to 0? By adding electrons. How many? 3. So there's the 3 electrons. Now, let's double check this. Here we have electrons as reactants in the reduction half. So that is a good deal. Alright, the oxidation half. If the manganese was reduced, then the sulfur must be the one that was oxidized. So we'll start out with that as our half. Sulfite goes to sulfate. Balance any elements that are not oxygen or hydrogen, but we don't have any of those, except for sulfur, and there's 1 on each side. So done. Balance oxygens by adding water. We got 3 on the left and 4 on the right, so we need 1 more oxygen on the left. So 1 more water on the left. hydrogens, 2 on the left, none on the right, so I have 2 H pluses on the right. And finally, electrons. On the left, we have -2. On the right, we have -2 and +2. So we've got -2 on the left and 0 total on the right. Now, the point of the electrons is to make them the same. So we need to take the higher side and move it down to the lower one by adding electrons. So 0 is higher than -2, so we're going to add electrons on the product side. We need 2 of them to bring 0 down equal to the reactants, which is -2. So I have 2 electrons on the product side. And there's our oxidation half. Now it makes sense that the electrons are products because oxidation is losing them. So that would be the perfect place for the electrons in an oxidation half. Alright, now let's investigate how to put them together. So in the reduction half, we had 3 electrons that we were gaining. And in the oxidation half, we were losing 2 electrons. Remember, you had to lose and gain the same amount. So I'm going to multiply the reduction by 2, because 3 times 2 is 6. And multiply the oxidation by 3, because 3 times 2 is 6. So there's both of those multiplied out. Remember to multiply everything in the reaction by whatever value you choose. All right, now let's put them together. So we've got our 6 electrons on the left and right that are going to cancel. But we also may have some other stuff that cancels. Let's see. I see 8 hydrogen ions on the left and 6 on the right. So what can happen is these 6 can cancel and 6 of these can cancel. So we'll be left with 2 of those. And then I see 3 waters on the left and 4 waters on the right. So these 3 waters can cancel and 3 of these can cancel. And I'll just have 1 water left there in the product. So electrons should always, always, always cancel, and then other things may cancel as well. And they may cancel partially, like we see here, or you could have 3 waters on each side, for example, and they can cancel completely. So in our balanced equation, you see we only have 2 hydrogen ions on the left and only 1 water on the right due to those cancellations. But everything else just comes down into our reactants and products because it didn't cancel. So there is the balanced redox reaction if we were in acidic solution. But it said we were in basic solution. So we have to take one more step. In this last step, and we only do this if we're in a basic solution, we have to account for the fact that basic solution has an excess of OH, not H+. So we add OHs to eliminate any H+. And just like in math, anything we do on the left, we have to do on the right. So in this case, we had 2 H+ in our final reaction. We're going to add 2 OHs to both sides to account for those 2 H+. So we add 2 OHs on the left and 2 OHs on the right. Now, what do you think OH and H+ do when they get together? Think about it. HOH. What is that? HOH is, of course, water. So when we combine these two, we are in fact making 2 waters. So in basic solution, you add OH on both sides. On the side where the H+ is, it's going to combine with the H+ to make water. So if you have 5 H+, you add 5 OHs, you make 5 waters. Here we have 2 H+, we add 2 OHs, we get 2 waters. Over here, the OHs have nothing to combine with, so they're just going to be included as a product on this side. Now that we have 2 waters, though, we have to double check because there's still a water over here on the product side. So this water on the product side can cancel with one of these waters on the reactant side. So we'll just be left with 1 water, and then we have this new product with our 2 OHs. Alright, So there is your final balanced redox in basic solution. All right, the last thing we want to talk about is something called a redox titration. A titration is used sorry for that interruption. Siri thought I was looking for something and she started talking to me. Anyways, picking back up here on redox titrations. A titration in general, so that's a key vocabulary word you want to underline, highlight, star, is a method that we use to determine the concentration of an unknown. So a redox titration in particular is used to determine the concentration of some species that we're oxidizing. So we have one solution with a known concentration, and we're going to add it to a solution of unknown concentration. And this color change is going to occur when we reach what is called the end point. Now, hopefully that color change is occurring at what is also known as the equivalence point. And the equivalence point is when the number of moles of the species being oxidized and the species being reduced are equal. Okay, so let's look at some key things here. So we'll go back and underline. We're determining the concentration. Okay, that's our goal in a redox titration or any titration. And we've got something that has a known concentration, and we're going to add it to something that has an unknown concentration. When we see the color change, we'll know that we've reached what is known as the end point. And the end point is what we see with our eyes, but it's signaling something deeper in the chemistry. So end point is just vocabulary for you see it with your eyes, but it's telling you that you're at what is known as the equivalence point. And this point occurs when you have equal number of moles of the one being oxidized and the one being reduced. And when we say equal moles, it may not be like you have 1 mole and 1 mole, but it's going to line up with whatever the balanced equation says. So I want to add that here because they may not be equal in terms of 6 is equal to 6, but they're stoichiometrically equal according to the balanced equation. So I'm just going to type in here if it'll let me. According to the balanced equation. Okay, so again, the equal that we're talking about there may not be what we would normally think of as equal. Sorry, I'm not gonna, this is not cooperating. But if you want to jot that down on your paper there, when we say equal, we're talking about according to the balanced equation. So if it's a 2 to 3 ratio in the balanced equation, then the equivalence point is when it's a 2 to 3 ratio. If it's a 2 to 1 ratio in the balanced equation, the equivalence point is when we get to that ratio. So equal is according to the balanced equation. I just want to clarify that. All right, so here's an example of a redox titration. So in this solution, that's not my marker. In the solution down here, we have an iron solution, which is one of our reactants. And it has an unknown concentration. And then we have another solution, and this time it's permanganate. Notice it's called potassium permanganate, but the potassium is a spectator, so permanganate is one of our reactants, and it has a known concentration. So that's one of the keys to a titration. You have one reactant with a known concentration, one reactant with an unknown concentration. You'll notice that the permanganate has a purple color, as it is in the, what do you call this thing? It is a burette. Okay, so in the burette you can see that it has a purple color. Now as you add it to the iron, it'll react with the iron to form these 3 products that you see. And in these 3 products, your manganese plus 2, one of the products is colorless. So every time that purple solution hits the flask and reacts, it's going to go colorless, 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 until you reach the end point, and that's when you see the solution change to this pink color. And the reason that's happening is because there's no more iron left to react, it's all reacted, so that one drop of this permanganate has nothing to react with, so it stays purple. So we see that purple color down here now, because there's no more iron for it to react with. When we see that purple color with our eyes, we know we've reached the end point, which is also the equivalence point. So we can go back from there and we can look and see what volume of KMnO4 we added. Okay, so I'm looking right here. We can look at where we started in the burette and where we finished, and we can calculate how much KMnO4 we used. From there, we can find the moles of MnO4, and from there, we can find the moles of Fe plus 2, because we know that they should be in the same ratio as they are in the balanced equation. So when we find moles of MnO4, if we're at the equivalence point, then we should have 5 times the moles of Fe, because according to the balanced equation, it's a 1 to 5 ratio. All right, so to summarize this lesson, make sure you know the extra step that you would need to do if you were balancing in a basic solution. From the previous lesson, make sure that you can identify which species is oxidized and which one is reduced, that you can write half reactions following the steps, and that you can put them together. And then finally, make sure you have a basic understanding of a titration. What is an endpoint? What is an equivalence point? What do we know? What do we not know? Okay, we'll pick up by doing one of these labs together, and from this lab we'll be required to find the concentration of the unknown species.